Dear students, welcome to Atoms to Infinity. Today we're going to do a P4 worksheet on waves, general properties of waves, whatever the name is in your book, in your textbook. And this worksheet is basically related to the extended syllabus. Right, let's start from the question number 1. We have question number 1 as there is a figure 6.1 and it shows a scale diagram of plane wavefronts approaching a gap in a barrier. So there is a barrier and there is a gap in it, and these are the direction of all the wavefronts. And it basically asks us draw a pattern of the wavefronts after the wave has passed through the gap. Now we know that when a wave passes from a narrow gap, it spreads around it. So that would be like, at least we would draw 3 wavefronts. So these plane wavefronts would be converted into these circular wavefronts. That's how it is done. Right, in part B, the wave approaching the barrier has a wavelength of 2.5 centimeters and the speed is 20 centimeters. We would have to calculate the frequency. Now, students, in my previous worksheets, I have told you that there is an equation called wave equation which relates velocity or speed, frequency and wavelength of a wave like this. So we have to calculate the frequency. So frequency will become the subject of the formula and our equation will become like this. Let's plug in the values. We will not convert these units because centi and centi will be cancelled. Alright, the speed is 20 and here the wavelength is 2.5. So we'll see what answer does it give us. Do calculate it with the help of your calculator. It's basically 8 Hertz. So it is 8 Hertz. There we go. In question number C, state what happens if anything to the frequency of the wave when it passes through the gap. Now I've told you that several times. Frequency of the wave remains the same because it only depends upon the source that produces only depend upon the source. I believe that that answer is correct. Now let's go to the question number D. Now after that our question will be completed. Explain in terms of diffraction why a car radio may pick up low frequency radio signals but not pick up the high frequency radio signals when the car is behind the hill. So here's something that is happening. So if we consider that this is a hill and here we have a car. So do you know cars have those antennas like this in their in the back side they have that sort of an antenna which is like in the air and it catches all the waves. So here are some radio waves which are about to hit that hill. This is hill. Let me just write it down for you. And if you see, all the high frequency waves will be reflected back because of this hill, whereas the low frequency or high wavelength, those will be diffracted and those will be received with the help of this car antenna. So let's write the answer. I hope you understood the situation. Let's write the answer here. The high, or you can say low frequency radio waves have higher wavelength. Let me just do this. It will help us a lot. Higher wavelength, and these waves are spreaded or bended easily. Right, let's do this. Easily. Therefore, the car radio will pick up these radio waves of higher wavelength because these bend easily. Let's just write it again just to endorse the concept. These bend easily. Right, this is the end of the question number 1. Let's go to the question number 2. Here we have water wave in a tank that travels from a region where speed is faster. So this is a deep region. I'm just going to write deep here. The density is higher here, and this is shallow. So we know that in a deep region, the speed of the wave and wavelength of a wave are really higher as compared to the shallow. It's totally opposite in the shallow region. So the speed of the wave faster in the region, right? This figure is 1/4 scale diagram that shows a wavefront, right? Now take measurement from the scale diagram. Now here's the scale is given. In the scale, 1 centimeter is basically 4 centimeter in real life. So in order to like calculate, let me just give you guys a simple example. All of these are wavefronts, and the distance between two wavefronts is basically your wavelength. Now if wavelength is 2 centimeter, so you would have to like multiply this 2 with 4. So actually the wavelength is 8 centimeter. So whatever that is, just take your scale and measure it. That would be wavelength. Now since the wavelength is given, you would have to calculate the frequency. So frequency would be like velocity or speed of a wave divided by the wavelength. Wavelength would be found here. Whatever the number that is, just multiply it with 4. I don't have a scale here right now with me, but I've told you the basic idea. The speed is given, by the way. The speed is 0.39 meters per second. And that's how you can calculate the frequency of this wave. Right, now in option B, in question number B, draw lines that indicates the position of the wavefronts of the water wave in the slow region. Right, here's something that you will have to learn as a rule. I will explain the reason as well, but let me just write the rule first. We would write the rule like this. I hope you would understand. When waves travel from dense region to rare region or medium, so these waves would bend away from normal, okay, and vice versa. Let's just write and vice versa. Now that would mean that if a wave is traveling from a rare medium to denser medium, so it would bend towards normal. But right in our case, if we draw a normal here like this is our normal, this is our normal as well, normal. So all of these blue lines are normals, alright? These are mathematically imaginary lines that we draw for our simplicity. Now the water wave will be like bending away from it. You see, these all waves are bending away. So these red are basically red lines. These are basically the waves, independent waves, which are bending away from the normal. So yeah, these are the incoming waves, these are the outgoing waves, or you can say refracted waves. So refracted waves are basically bending. So that just remember this as a rule as well, so that you can understand, because this rule is very important. Right, now in option C, state what happens to the frequency of water waves that passes through the slow region. It passes through the slow region, so this is something that we would always understand. This is very simple because I've already told you this. The frequency will remain the same. And why is that? Because frequency of a wave, because it depends upon the source that produces it. Okay, let's just correct the spellings for the frequency. Right, now why I'm saying this, imagine this is a ripple tank. A ripple tank is a device that we use in order to study the properties of the waves, mainly water waves. Now this is something amazing about it, that we have some sort of an oscillator here. We have an oscillator which is basically a motor, so it would be like creating ripples in the ripple tank, and that frequency will not change since we are not changing the source. Now in question number 3 part A, we are shown with a metal strip which is at the Y. It was initially at Y. Then what we did, we took it all the way to Z and left it. So it started to like vibrate like this, in this direction, like this. So I hope you got the basic idea. Let's see the frequency of the vibration of the strip. Now how can we basically say that what is going to be the frequency? It will be just number of waves frequency of the vibration of the strip. So a number of waves which are, this is per cycle. The wave would start from here. It will go to this position. So it's 0. Consider it 0 degree, consider it 90 degree, and this 180. Then at the same time this will become to 70, then 360. So it's like this. It's basically a wave, but drawn. So that's how it is. That is how the wave is traveling in this direction, and that metal strip is also vibrating. So how are we going to define this? How are we going to do this? Let's see. The number of waves or vibrations, let's write vibration, that would be accurate. Vibrations per second will be the frequency. That would mean the number of complete cycles. Okay, complete cycles per second. Now how this would happen? Well, it would start from Z. It will basically go all the way to Y, then to X. It will not stop at X, it will come down. So Z to Z, that is a complete one vibration. Let me show you here. First it will start from Z, it will go to Y, then it will go to X, then it will come back to Y, and then it will come back to Z. So the number of time it repeats this cycle per second, that would be the frequency. Now the amplitude of the vibration, or we can also write this, frequency will be Z to Z per second in 1 second. There we go. The amplitude of the vibration. Now amplitude is a maximum displacement. Here is the maximum displacement, either from Y to Z or Y to X. So let's write it down. The distance, let's say not distance but displacement, it's a very small one, so we're going to do this with displacement. The displacement between, it was at Y, right? Y to Z, or from Y to X. From Y to X will be the amplitude. Or the maximum displacement. Just don't write it, I believe that's enough. Right, in question number B, part B, there is a person who is standing. Now here are two buildings. Buildings are A and B, and the distance between these two buildings is 99 meters. And that person is standing at 33 Mach toward this building A. Now the distance is 33 meters, speed is 330. We would have to know what is the first echo. Now in my sound worksheet, I already told you that you would have to apply that formula in order to find the echo. So just remember this. Echo would be like when this person is speaking. So wave would travel 33 meters to this wall, and then it would come back by covering the same 33 meters. Okay, so the speed, what do we have to find? We have to calculate the time interval between the clapping of his hand and hearing. Alright, so T will come here. That will be just 2D divided by V. Let's plug in the values. It's 2 into 33 divided by 330. Now let me calculate the time interval for the first echo. So that is basically 66 divided by 330. 66 divided by 330, which is 0.2. That will be the time taken for first echo. Now in order to find the third echo, we will just multiply the first echo with 3. Let's multiply this. That would become 0.6 seconds. There we go. That is the time taken for the third echo. Now write down an approximate value for speed of sound in water. Well, in water it is around 1500 meters per second. And in steel it's around 6000 or 5000 meters per second. Do check it on the internet because that value can change. Right, in option D, in part D, there is a dolphin which is producing a sound of 95 kilohertz. Using your value from C, okay, now wavelength of the sound. Okay, we would have to dolphins are in water. So speed of sound in water is 1500 meters per second. Frequency is given, and we would have to calculate the wavelength. So wavelength would be
1500 divided by 95,000, because it's 95 kilos, so it's 95,000. So let's calculate the wavelength. The wavelength
will be 1500 divided by 95000.
that is
Very small wavelength, and
that makes sense because of the frequency is very high.
0.017
meters. That
is the wavelength.
Now in question number 4, there is a loudspeaker which is producing sound, and those sound waves are traveling in air toward a solid wall. Now there is a solid wall. Show compression. Right, there are all of these are compressions. These solid lines, these represents the compressions, independent compressions, and the distance between two adjacent compressions is basically the wavelength. Now what is meant by compression? Let's first write this one. What is meant by compression? It's very easy. Right, now the compression compression is a region where air particles are closed and compressed. Okay, now let's go to the part B. It says the distance from point P to Q is 8.5 meters. It takes 25 milliseconds for the compression at P to reach Q. Now we would have to find the wavelength. Now it's very easy, because first of all we would know the wavelength. It's very easy to calculate, because right now what we see here, that is a distance for 5 wavelengths, I believe. Yeah, 1 2 3 4 5. So that distance from P to Q is the distance of 5 independent wavelengths. So let's just find the distance of one wavelength, or you can say the one wavelength. That would be divided by 5. Let me see what value does it give us to us. So it is 8.5 divided by 5. It is 1.7. So the wavelength is 1.7. Right, let's write it down here, 1.7. Now the frequency, let's see, that is a distance, V equals to D over T. By using this formula, by using this distance and this time, we can find the value of the speed of sound. Now let's see, 8.5 is the distance, 25 milliseconds, that milli can be converted like this. Now it is converted into meters. Now let's see what is the actual value, what is going to give us, what is the complete answer. Let's see. So it's 25 millimeters. Let's see. Zero 0.025. Okay, 85. 8.5 divided by 0.025. So the speed of sound that came out to be 340 meters per second. Now we have speed, we have wavelength, we can find the frequency. So frequency will be speed over wavelength. 340 divided by 1.7. The answer is going to be very large, I believe, because the wavelength is very small. So it is 340 divided by 1.7. Yeah, 200 hertz. That is the frequency of all the sound waves which are produced by this loudspeaker. Now as it strikes the wall, the sound reflects. Complete 7.1, figure 7.1 to show the positions of 3 compressions of the reflected sound wave. Alright, now it will come back in this direction, reflected, totally reflected. So I'm going to draw the wave fronts with the red color. So no, let's change the color to this one, whatever color that is. So that is the direction of all the reflected sound waves which have been reflected by this solid wall. Right, part C is done. The loudspeaker is immersed in water when it continues to produce sound at the same frequency. Okay, now the frequency is same. State and explain how the wavelength of sound wave in water compares with the wavelength determined. Right, now all we need to do is this, speed in water, that is 1500 meters per second. Frequency does not change, so frequency is 200 hertz. We would have to see the wavelength. So wavelength would be equals to 1500 divided by 200. So that is basically 7.5. So if you see this, the wavelength has been increased. In air, the wavelength of sound was 1.7 meters, but in water it is 7.5 meters. So we will just remember this value. Let's just write the answer here first. Right, there we go. Because of higher density of water, the speed increases, okay, and wavelength as well. That is because speed and wavelength of a wave are directly proportional to each other. There we go. So you can say speed of the wavelength in air was 1.7 meters, but wavelength in liquid or water, that is 7.5 meters. That is the best comparison. Alright, now state how longitudinal wave differ from a transverse wave. Very easy. In longitudinal waves, the molecular vibration is parallel to the direction of propagating waves. Alright, now that's it. We can write in the next line. Let me just correct this. Whereas the molecular vibration is vertical to the direction of wave in transverse wave. There we go. Now the option is completed. Let's go for the part B. A sound wave of frequency 7.5 kilohertz travels through a steel beam. Okay, the speed is given 6100 meters per second. The frequency is also given. Calculate the wavelength of the sound. Now it's very easy. I'm not going to calculate it. It would be just 6100 divided by 7.5 multiplied by 10 raised power 3. Now just write these values into your calculators and you can calculate the wavelength. Now the sound passes from the end of a beam into the air. The effect of the speed of sound. Now speed of sound would decrease, of course. Speed would decrease. The effect on wavelength would decrease as well. If you remember, I've told you that already, that speed and wavelength are directly proportional, and sound is faster, or the wave is faster in a dense region, whereas air is a rare region. It's less dense than at least water. Now two types of seismic waves are produced by earthquake. They are called P waves and S waves. P waves are longitudinal and S waves are transverse. Explain what is meant by the term longitudinal and transverse. Well, you can calculate it. You can basically write it because I've explained this question in here. Here you can see the difference between them in question number 5 part A. The option is same, the answer is same for both of them. State another example of a longitudinal wave, that is sound. Sound is a typical example of a longitudinal wave. A transverse wave, it's light, and it is a typical example of transverse wave. A seismic wave has a speed of 7.2 kilometers per second and frequency of 30 hertz. Now let's calculate the wavelength. Now wavelength would be nothing but 7.2 multiplied by 10 raised power 3, because it's kilo, divided by 30, and that would be wavelength. Now, in part B, the figure 5.1 shows an electric bell ringing in a sealed glass chamber containing air. There is air right now in it, so bell would be like ringing and we would be able to hear it. A student hears a bell ringing. There we go. The air is then removed from the chamber. State and explain any change in the sound heard by the student. Okay, now that is very easy because sound requires a medium to propagate. If there is no medium, or the medium is like slightly going away, if the air particles are leaving the medium slowly, so sound will be faded and fainter. Okay, so the student will not be able to hear any sound because sound depends upon the medium for its propagation. Propagation. Since the medium which was air is not available, so there would be no sound. There we go. That was our question. Let's go to our question number 7. Now, figure 5.1 shows an aerial view of all the wavefronts passing from the open sea into an outer harbor. Now that these are harbor walls, you can see the difference, the length between them. The gap is quite wide. So all the wavefronts which are coming in this direction, they have a very low bending, very low spreading. However, here the gap is very, very small. So all of these waves, when they will approach this barrier, they will be like spreading prominently. So you would be like able to see the spreading more prominent because the gap is now very smaller. Now name the process that occurs. Okay, that is diffraction. Very easy. There we go. Now on figure 5.1, carefully complete the wave pattern as the wavefronts progress through outer harbor and into the inner harbor. State the rest of the wave pattern in the outer harbor and 3 wavefronts in the inner harbor. Right, now that would be like complete here like this. Okay, and basically that question is done. Alright, now in part B we have a figure 5.2 that shows an aerial view of the wavefronts in deep water approaching a region of shallow water. Now I've told you that as a rule that you would have to like take a normal here. That is normal, that is normal, that is normal, that is normal, and that is normal. Let me just make it more normal which is like 90 degrees. Alright, now we would take another color just to show that how the waves would travel. So I told you when waves are going from a dense region to a shallow region or a rare region, these waves would bend away from the normal. So that is how this wave would be like traveling. Okay, that direction shows the wave. So use scale to draw like proper, but just remember one thing, that all the waves would be like going away from the normal. So that would be like direction like this. Oops. Let me just redraw these both. First one, and that the second one, and that is the third one. So that is how they would travel. So imagine here is the boundary of a medium. So that is deep region, that is shallow region. Name the process that occurs. Okay, now this is refraction. We already know that refraction is a process in which a wave bends away from its original position. It changes its path. And in part 2, complete figure 5.2 to show the possible position of the 5 wavefronts into the shallow water. Right, now let's just take that is 4th and that is 5th. There we go. Now this worksheet has been completed. It was very interesting. The questions were not very tough, but yeah, for all the students these may be tough. I mean, of course not for me. However, this worksheet is done. If you don't understand any explanation, if you don't understand any question, just tell me in the comment. I'll repeat it over there. You can contact me, by the way, with the help of the comment, and I'll explain each and every concept again with better reasoning this time. So this was the end of the worksheet. I hope it was worth of your time. Now with that, I would take my leave, and I'll meet you in another worksheet. Do subscribe my channel and like the video. Dear students, goodbye.